So today we are going to review the notes that I sent you. So it's supposed to be a replacement for the session on the 22nd December, and the topic will be on the Lagrange interpolation. So if you read the note before, given a set of data, as in the explanation there, there's always a unique polynomials of n order that will pass through all the data points. So this is the foundation of Lagrange interpolation. And what I'm going to do here is not to read all the notes for you again. That will be repetitive. What I'm going to go through with you today, instead of being repetitive, I'm going to show you more of the example on how to use the Lagrange polynomial. Now before that, let's have a look at the definition. So you have the polynomial here, which is P here, and then you have the summation of all the data points. So the index here is generally it starts from 0, but it can also start from 1. But if you start your definition from 1, then the order of back here, the order will be of n minus 1. So that's why we are using the commonly used index notation from I equals 0. So let's say you have n points of data, which is actually just a set of x0, f0. It's just a set of these pairs, and the interpolation is defined as a function li x multiplied by fi, which is the data at x I. Now this li is called the Lagrange basis, and the definition is here. So this is a p, you call it p, so it's actually a Greek word for product, so that's why you use this symbol. This is actually a p in Greek, in the Greek letter. So you have the j, from j until the n, not n as in ending, the n as in the letter here, and you multiply all of them, x minus xj divided by xi minus xj, provided that j is not equal to I, because that will cancel out the denominator. So you have a division by 0 if I equal to j, so you have to skip that. Now the simplest example will be the 2 points data, which is just a linear approximation. So in this case, we start our I again from 0 and until 1, so we have that 2 data points. So x0, f0, x1, f1. So if you expand the summation, so you have L0x multiplied by f0 plus L1x multiplied by f1. And if you go again by the definition of the Lagrange basis, so you have x minus xi divided by x0, okay, here again from 0 minus x1, and L1 is from x1 minus x0, again not the same I, not the same subscript I, and x minus x0. So if you combine the basis with the data, that is f0 and f1, so you have the polynomials. Now this is actually just a linear approximation of the 2 points, which I think by now should be a common sense to you. If you have 2 points, then the most logical way to fit the 2 points would be a linear equation. So if that the special case is where the distance between point x0 and x1 is h, and it's of a constant, okay, so you can write it down, ending up just like the normal linear equation that you usually found. Now in the case of 3 data points, So 3 data points. Again, if you expand them, expand the basis, you calculate the basis using the basis formula. Okay, again observe no same subtraction at the numerator, okay, to avoid division by 0, and then you end up with the whole equation, the whole Lagrange polynomial as in here. And the numerator, if you observe them carefully, so this is actually a quadratic function. So you have x multiplied by x. If you expand them, it will be x squared. So again, 3 data points, quadratic equations. So that is the meaning of a unique a unique polynomial. So this is the case, a unique polynomials, okay, that unique polynomial that passes through all the data points. So that's the meaning of that explanation. That's the that definition. Now, if you look at it from terms of ax squared plus bx plus c, so you have 3 unknowns, a, b, c, and you have 3 data points. Okay, 3 unknowns, 3 equations, so you can solve for a, b, and c. Now, if let's have a little bit discussion about the Lagrange polynomial. Because it tries to fit the data, because it creates a polynomial that fits all the data, it is susceptible to oscillation in the function, in the interpolation function. And this phenomenon is known as the Runge phenomenon or Gibbs phenomenon in physics. They are the same. So basically what the phenomenon means is, as you try to fit everything, okay, as you try to fit everything, sometimes the data just would oscillate. Instead of, say, suppose that this is the real data, this is the real line, so this is the theoretical, okay, and this will be the Lagrange polynomial fitting. Now, in reflecting with the current trend, so the Lagrange polynomial problems is that it is prone to overfitting. So this is the case of overfitting. Okay, which is not clearly not the solution that we want. So that is something you need to be careful with when implementing the Lagrange interpolation or the Lagrange polynomial. Next up is the Newton polynomial, which is just a variation of the Lagrange polynomial. And to keep things what they call it in a applicable manner, in something that you can apply directly, so we are going to restrict our discussion to up to second order. So okay, second order polynomial, we're going to stick to that. So this is the case of ax squared plus bx plus c, okay, because usually this level of interpolation is usually enough for most of engineering application. So given a data set of I minus 1 and I minus 2, or I minus 1, I and I plus 1, and one more restriction that we will impose specifically for this course is the equidistant requirement. So you have xi minus xi I minus 1 equal xi plus 1 minus xi minus 1 minus xi minus 2, all of them are of equal values. Now, for the interpolation, for the Newton polynomials, the formal definition of the polynomial is qx. We're going to use the letter q here. So fi, so this is the center of our interpolation, meaning that this will be our reference point. Basically, in the quadratic equation, this will be our c. Okay, fi is our c. Then plus a, x minus xi, again our reference at I, plus b, this is the coefficient that we need to find, that we need to resolve. X minus xi, again taking from the first terms, and multiply by x minus xi minus 1. So from this data point, I minus 1 and I minus 2, we will pick a point starting from our reference I, and then I minus 1. Okay, so now what we have to do is to solve for a and b using the values from xi minus 1 and xi minus 2, which in our case will be fi minus 1 and fi minus 2. Again, two unknowns, a and b, two equations from fi minus 1 and fi minus 2. So if we do the algebra one by one, so we'll end up with our a equals fi minus 1 divided by h, and our b equals to fi minus 2 fi minus 1 plus fi divided by 2h squared, and our polynomials becomes qx equals fi plus a. So this is a and this is our b. Again, 3 data points equals to will bring you to quadratic equation. Now the advantage of the Newton polynomial is that you can add more points, okay, without the need to recalculate the whole polynomial, because by adding another point, let's say so you have a, b, and another c plus and another, let's say, plus c. So all you have to do is just x minus xi multiplied by x minus xi, xi minus 1 and xi minus 2. So all you have to do, if you have another extra point, so for this point I minus 1, I minus 2, so let's say you have another point I minus 3, all you can do, or you can easily calculate for c by just adding up the polynomials here. That's the advantage, and it is the final form is equivalent to the Lagrange interpolation, except that the algorithm is easier for you to work with. But of course, the general form is the Lagrange form. Now, that's one point, and the other one is that you can shift the center. For example, in this case, we have I as the center, but let's say we want to shift the point from I minus 1, I minus 2, we want to shift it by minus 1. So our first data point will be I minus 1, our second data point, let's say we want to shift, this is a plus 1, sorry. So let's say we want to shift this point to plus 1. So you have I will be I plus 1, I will be I plus 1, I minus 1 will be I, and I minus 2 will be I minus 1. So all you have to do, if you shift it, you only have to shift the coefficient. So you have A equal fi plus 1 minus fi instead of fi minus 1. And the same goes for B. Instead of fi minus f2, you have fi minus 1. No, instead of minus 2 fi minus 1, you have 2 fi. And the same goes here. So instead of fi, you have fi plus 1. And the shift also is needed for the multiplier. So instead of here, so I minus 1, if you shift it, you have x minus I. If you shift it, you'll get xi plus 1. So the other way to look at the Newton polynomials is that it can be obtained by a divided difference. We are not going to go into too much details regarding this approach, because it would just be a lot easier for you to just solve for a and b. But the idea here is the same. So if you take the difference, that's why they are divided difference. So if you take the difference between I and I plus 1 to be d, large D, so we use the d to show it's a difference. So at this number 1, this 1 represent the level, and I represent the what do you call it, the range, the section. So you can use your own definition for the section. So in this case, the commonly used section definition is from node I to I plus 1 will be a section of I. So that's the most commonly used definition, but you can also always shift it, doesn't matter as long as you understand it. And I minus 1 will be the section of I minus 1. So this section A, where you have this point A, you can calculate the difference. This is the difference, which is just the slope actually, okay, for an equidistant data. And for di minus 1, so you have fi minus 1 divided by h. And for second order, which is why for second differentiation, you have 2. So this is d2i, which is basically the same as the terms for b here. Okay, what you do is you use back at level 1. So this is level 1. So this is level 2. So you use back the result from level 1 and take the difference equation. So you have the second level of difference equation. And you can reconstruct it back to be just like the Newton polynomials that I've shown you before. Now, this is where, in our case, the physics is more important than the maths. So if we are looking to interpolate the point A, so the best polynomials would be using the di1 instead of the di minus 1. And the same goes for B. It is better for us to take the slope of di minus 1 instead of di. Okay, and by doing that, you have two different set of interpolation that you can freely use, each with a different value because you shift the position of your reference. And moving on from this chapter, we will look into some simple numerical differentiation. Okay, so this will be preparation for finite difference method and finite volume method. And Newton-Cotes integration is the general form of numerical integration, but we will focus directly on the Simpson's rule. So specifically, we will focus on Simpson's one-third rule. And this is where the Newton polynomials will come in handy. Newton polynomial. The Gaussian quadrature is something special that deserves another video on its own, a more structured explanation. which we will cover later, and this will come up in our quiz. So this will be in our quiz. Okay, and this will be in our assignment because it's long, and this also will be in our quiz because it's short. Okay, and I will introduce you to the Runge-Kutta, okay, or the RK integration for just one simple ordinary differential equation, just one sample, the simpler one. And we will only discuss some very simple application in for FDM and FVM in PDE, and that will be the advection equation only. So that's it for this time. See you next week. We will have our live session next week.